In this video, we're going to look at a little bit more on how ionic bonds actually form and then some characteristics of ionic compounds. So, an ionic compound is an electrically neutral compound, and it has positive and negative ions. These compounds are held together by an electrostatic force. An electrostatic force is simply a force that's created between the attraction of a positive and a negative substance. So in this case, that would be an ion. So an ionic bond is the electrostatic force that holds ions together in an ionic compound. The strength is going to depend on the magnitude of the charges. So that means that the bigger the charge, the stronger the bond. So an ion with a +2 charge is going to create a stronger bond than an ion with a +1 charge. And this is an inverse relationship to the size of the ion. So that means that the bigger the ion is, the weaker the bond will be. And that's because the distance between the nuclei increases as the ion is getting bigger in size. So that means that sodium is a smaller ion than the cesium ion, even though they're both +1s. So sodium will have a stronger bond because it is a smaller ion. We show the transfer of electrons in ionic compounds with electron dot diagrams. And so we can see that with sodium chloride. The Na has the 1 valence electron and chlorine has 7. And we can see that that 1 sodium electron transfers to that chlorine ion so that they both actually have a complete octet. So when we see our final product here, that sodium ion doesn't have any electrons surrounding it, this is because the energy level that originally contained electrons or valence electrons is now empty. So by not putting any electrons around that sodium ion, it shows us that that energy level is now empty. So when we look at magnesium, magnesium has 2 valence electrons, so that requires 2 chlorine ions. And so each chlorine ion will accept 1 of magnesium's 2 valence electrons. So again, we show that as magnesium, not magnesium 2+, having no valence electrons because that energy level is now empty. And then the chlorine satisfies that octet. So we refer to a ionic compound, or one piece or one part of an ionic compound, as a formula unit. This is the lowest whole number ratio of the ions present in the ionic compound. This will always be the empirical formula, like we talked about from chapter 7. So the formula unit for sodium chloride is NaCl, and so we say that this is one formula unit. If we had 2 NaCl's, this would be 2 formula units. And so you can abbreviate that in your assignment as FUs, that's fine. Ionic compounds, they form an extended 3D array. We call this the crystal lattice. And this is pretty much just a fancy way of saying that these ions, these cations and anions, arrange in a very specific pattern. They alternate between the positive and negatives, and they're going to give you this crystal lattice, and this crystal lattice will be a very geometric shape, meaning that you would be able to predict the next ion in the pattern. These crystal lattices help to maximize the attractive forces between those oppositely charged particles, and there's two ways to show this. You can use the ball and stick diagram, where you use, in this case, there are these red lines to indicate the bond between the cations and the anions, or you can use the space filling diagram, which eliminates the red sticks and the bonds are just assumed to be there. And so both of these diagrams are showing you NaCl, and you can see that they alternate a chlorine and a sodium, chlorine, sodium, chlorine, sodium, chlorine. So if it's kept going, you know that this next one would be a sodium ion. And so these are just two ways to show those crystal lattices. A coordination number is the number of ions that immediately surround an ion of the opposite charge. So this is a ratio of the ratio of coordination numbers must be the same ratio as the formula unit. So if we look for the coordination number of the sodium or the purple ions, it usually works best to locate an ion in the middle of the lattice. And so here we have a purple one, and this is really just, you count the number of 1, 2, 3, 4, 5, 6 bonds. So there are 6 bonds coming off those sodium ions. And then again, if you were to repeat that same process for a green or chlorine ion, you would see, so if I pick this one in the middle here, there's 1, 2, there's 3, 4, 5, and you can't see the 6th one because it's behind this chlorine ion, but it is also 6. And so what we're saying about the ratio of coordination numbers, it has to be the same ratio as a formula unit. So our formula unit has a 1-to-1 ratio, so that means our coordination numbers must also have a 1-to-1 ratio. And so remember, ratios have to be in the lowest terms, and so our 6-to-6 ratio can be reduced to 1-to-1. So to practice that again, if we look at the coordination number here for cesium, cesium is in orange, and so we look at how many bonds come off the orange. 1, 2, 3, 4, 5, 6, and then there's 7 and 8. And so I know these are kind of hard to see, but you just have to kind of really look where they're bonded. So the 2 in the back corner, they try to show you that as best as possible. So then your green coordination number, or for around chlorine, again is going to also be 8. However, it's going to be much harder to see that because they don't show it here in the diagram. And so here your ratio of coordination numbers is going to be 1-to-1 or 8-to-8. And so since you can't see the 8 for the green chlorine, you would have to look at the formula for cesium chloride. So cesium is +1, chlorine is -1. Both of those numbers just come off the periodic table. So your formula unit is CsCl. So you know you have a 1-to-1 ratio, and so your coordination ratio also has to be 1-to-1. The last one we're going to look at here is titanium 4 oxide. Titanium is the gray, and the oxygen is the red. And so I think this one's a little bit easier to visualize. And so if you look at the gray, we have 1, 2, 3, 4, 5, 6. And so we have a 6. And then if you look at the red over here, we'll focus on this one as 1, 2, 3. It'll be 6-to-3 or a 2-to-1 ratio. And when you look at titanium 4 oxide, Ti, it has that +4 charge. oxygens a -2, so your formula unit would be Ti 2O4, and when you put that in lowest terms, TiO2, and so that's your 2-to-1 ratio as well. So that does make sense. So then just some physical properties of ionic compounds. Their shape is very geometric or very orderly because of the alternating arrangement of the positive and negative ions. The color, any color that you would see in an ionic compound is going to be due to any transition metal. The strength of an ionic compound is due to the positive and negative attractions, so that positive negative attraction in the crystal structure. This gives ionic compounds high melting points, and so that means that it requires a lot of energy, so a lot of energy required to break the bonds. So, for example, your sodium chloride, your table salt, if you were to boil solid table salt, it would take up to 800 degrees Celsius before that sodium chloride would actually begin to boil. Ionic compounds are very brittle. That means that they have a tendency to shatter when they actually do break. So this shows you the regular structure of sodium chloride, very nice and orderly. And those positive sodium ions are separated the negative chlorine ions, and so they're not touching. They're as far apart as possible in that structure. But if something were to strike that ionic compound, notice how we now have the chlorine ions being next to each other, and like charges tend to want to repel. So now this repulsion force, we've got it here and here and here, is going to cause the substance to shatter. So this brings ions of the same charge near each other. And this repulsion causes shattering. This will, the shattering will break along smooth planes. Due to the regular arrangement of ions. Ionic compounds will also conduct electricity, and so if you have here just plain water, you're going to see that it's not conducting any electricity. It's not turning on this light bulb, and this would be your molecular compound. Water is a molecular compound. And then if you have just solid salt or any solid ionic compound, the positive and negative ions are fixed, and so they cannot conduct. It doesn't allow the movement of electrons. And that movement of electrons is what carries electricity. So here in a solution, the positive and negative ions move and it can conduct a current. So when you put, let's say, salt into water, what's going to happen is you're going to break apart the Na and the Cl ions. And so now we have that negative ion to help us conduct electricity. So the ions are free to move. And this only happens in melted or dissolved, if the substance is dissolved in water. So that's your quick overview of ionic compounds and how ionic bonds form.